All right, Delaney, can you see that okay?
Is this big one Santa's flag?
It looks like it. Does it look like a bunch of rocks all stuck together?
Yeah, I can see it.
Okay. Good. How are you, Jonathan?
I'm good this morning, actually.
Thank you. You're welcome. Thank you. This is not going to be used as a grade. This is going to be used to help you take notes on this, so you can hold on to it.
Your family can feel it.
Thank you. I was really excited about that.
The
Like,
Beyonce win.
I saw that. I know, like my dad holding my dog. That was funny. That like I got the win here. I'm like, look at our hair.
I gotta see this picture now.
Oh, it's hilarious. All right. So the first thing I want you to take a look at is we have the geographic map of West Virginia. And what do you notice about the map itself, Lacey? And if you take a look at this, just tell me one thing you notice. All right, there's a lot of blue. All right, and the different colors represent the different ages of rock. And so instead of us, in geology, instead of just saying, oh, this is 300 million years old, we assign it an age with a name. It's kind of like, you wouldn't just say, oh, that's the 11th month. You would say it's November. So geologic time in West Virginia is only during the Paleozoic. All right, so I have a marker. Okay. I'll do something else. Hold on a second. We'll share. It's hard to tell. It's okay. I'll share my white screen so that. Okay. So let's talk briefly, very briefly about geologic time.
Is it on packet?
No, this will just be, yes. Yeah, this will be notes on your own. But I just want to go over geologic time because when you look at that map, you're going to see words like Permian, Pennsylvanian, Mississippian, things like that. And it won't make any sense to you unless we at least touch on this. So geologic time is broken down into really big eras. So eras are really long time spans. And then we're going to look at periods, which are a little shorter. But remember, when we talk about geologic time, when I say shorter, it might just be a few million years shorter. Okay, we don't discuss things in length of thousands of years until more recent time. But let me go through like what the eras are. When you read geologic time, it goes from bottom to top. Do you see one? Yeah. to the left. I love green. Yay! Thank you. This will be much easier. All right. So Delaney, I'm going to stop screen sharing for a second. So we have 3 eras in time, and they are the Paleozoic, and you'll understand why I'm writing like this in a second. The Mesozoic, oh geez, and the Cenozoic. Oh. Everything in West Virginia is in the Paleozoic. And when I'm saying everything, I'm talking about geology, with the exception of a couple of igneous events. But everything that we're going to talk about today in West Virginia is in the Paleozoic. And this just means ancient time. This is just middle time. And Cenozoic is recent time. In order for me to memorize things like this, I always come up with my own, mnemonic devices. So to me, all of the periods in the Paleozoic, so now we're going to look at the periods. We have the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and we'll get rid of that. And Permian. Now,
So that from the Cambrian, that's like lowest.
yes, this is the oldest at the bottom.
Okay.
It's always like making a cake. You can't have icing until you have a cake underneath of it. So technically the cake is going to be older than the icing. That's the same way sedimentary rocks are. Cambrian, Ordovician, and this is how I remember it. Campbell's onion soup doesn't make people puke. You can remember it any way you want to. That's just me. So when we take a look again, let me let Heather in. I'm ignoring her. So when we take a look again at this map of West Virginia, let's mute Heather. All right, so when we take a look again at this map, I want you to find something called the Precambrian. Whoops. And Precambrian just means, hey, I came before the Cambrian. Most of the time of the Earth is in the Precambrian. Several million years, well, a couple million years. So before life began. And then life begins as tiny little single cell organisms during the Precambrian. Then we get into the Paleozoic. These lines represent giant events that happen worldwide. And here we have something called the Cambrian explosion of life. Pardon me? that separates the Precambrian from the Paleozoic. And what happened was life evolved hard parts. We began to get teeth. We began to get shells. So more things could fossilize. So before the Cambrian, if you looked in the rocks that were Precambrian in age, very few fossils, except microscopic. And then something happened with the evolution of life that they developed hard parts, and now we can see fossils worldwide. So that's a big one. And I'm going to hop up here to the Mississippian real quick. This is West Virginia. It's covered in a shallow ocean. Nice, warm, shallow ocean. And we had, for millions of years, this nice little ocean going on. And as things died, they would float down and build up and build up and build up on the seafloor until eventually they lithified, which is just a fancy geology term for it turned to a rock. And so you get tons of limestone from these events. So like, if you ever wanted me to prove it, okay, Greer limestone, it right in Morgantown. Limestone comes from these ocean events. And so we have so much limestone all over the place. The Greenbrier, if you've ever been to Greenbrier County, there's lots of caves and sinkholes and things like that. That's all from limestone, and that's all because we were covered by an ocean. But let's take a look and see on your map how things kind of change as we go from the Panhandle all the way over to the Ohio River. So you see a tiny little bit of brown right there in the yellow. We actually have Precambrian rock. So it's more than 600 million years old over in the Harper's Ferry area. And then we have some Cambrian. And you can take a look and it tells you like how old these things are. And then the Ordovician, the Silurian is the purple, the deeper purple. Then you get the Devonian. And then you see, do you see how it is moving from, if you're looking at it, it's from the right to the left. We're going from the oldest all the way over to the youngest, which is on the Ohio River, all the way over to the Permian. And the way that they date these rocks is from the fossils that they find. So the way they get the ages of the rocks is from the fossils, because they know how old those are. They also use something called radiometric dating. You've probably had like carbon dating. If you've ever watched Good Murder and Mayhem on TV, you see, oh, we had to date these bones to see how old this woman was when she died. That's carbon dating. So they use radioactive carbon, carbon-14 to date bones. But things that are millions of years old, we need something bigger. And sometimes it's like lead and uranium and things like that. We use radioactive decay to date older rocks. All right, so that brings me to our West Virginia rocks. Because almost everything in West Virginia is sedimentary. Come on. Oh, gotcha. Thank you. Absolutely. All right. Wow. There we go. I'm going to ignore that too. So just you're going to take a look at these road cuts. And you know, if you're driving along the interstate, you see these, well, any road you drive in West Virginia, you see road cuts. And the first thing I want you to do is take a look at your lab handout that I gave you and just make some observations. Tell me what you notice about these road cuts. So those of you at home, they have pictures of rocks alongside the road. And they're just making physical observations about what they see. All right, Jasmine, tell me one thing you noticed. Okay, so we do. We have layers of rocks. And are they horizontal or vertical? All right, so we have horizontal layers. Hannah?
It looks to be like a pattern, like the rocks and then there's a slope and then like rocks and slope.
Okay, a pattern of rocks, then slope, and then that repeats. Okay. Aaliyah?
There's trees and plants growing on top of the layers.
All right, so we have trees or other vegetation on top of each layer. Anybody else notice anything? Yes.
I said it kind of looks like the hill is getting wider the higher up it goes.
Okay.
At least it looks that way.
Sure.
Look at the rocks are different colors.
Excellent. That's good. So Grace noticed the rocks are different colors. And that's going to come into play. Because do they all look like the same rock? No. And they're not. So here is what we usually get as a common list. There are different layers. Yep. The layers are different colors. Some layers, like you said, it looked like it's getting thicker or wider at the top. Yes, some of them stick out farther. You probably noticed this, but didn't say it. Looks like there's debris, like the smaller rocks that crumble and fall down at the base of the slope. The rocks are mostly horizontal. If you take a look, you'll see vertical lines in the rock. That's not a layer. Some of those lines, it looks like maybe where they've dug out the hillside. And so those are vertical lines. But also, if you look at the sample 2 outcrop, you'll just notice more natural vertical lines. Those are called joints. It's just where they kind of butt up against each other naturally. There's a slight dip to the rocks. So the rocks aren't perfectly horizontal. They're just slightly tilted a little bit. And some layers, of course, are thicker than others. So those are generally the observations we see in this. So what type of rock are they? Sedimentary. And how do sedimentary rocks form? Well, obviously they form from sediments. So what are sediments? We talked last time about igneous rock. Igneous rock breaks down, and those tiny little bits and pieces are sediments. Sediments can be things like sand, clay, gravel, and it's just all based on their size. Because we could have coarse sand, fine sand, pebble, gravel, and they're all carried away by wind, mostly water. Water plays a big part in West Virginia. So water carried most of the deposits that we see throughout the state. It can be deposited by ice. When we talk about ice, we're thinking glaciers, but not in West Virginia. I want you to write this down right now, and I want you to remember it for the rest of your life. Glaciers never made it to West Virginia. Glaciers never made it to West Virginia. It stopped. The biggest glacier that was here stopped roughly 6 to 10 miles north of our northern panhandle. In fact, there's a bank that we would take field trips to, and you can see the very last glacial grooves in the rocks up there. So that doesn't mean that we didn't get ice deposits, because it would wash into the river, which we now call the Ohio River. And so you get these glacial rocks there. The glaciers were never actually here. They also formed Glacial Lake Monongahela, which, how many of you been to Chick-fil-A right down from the Coliseum up in Morgantown? So that sits on, in fact, all of that area sits on Glacial Lake Monongahela. And there's just all this loose sediment underneath. They had to drill down 80 feet beneath Chick-fil-A when they were building it to anchor it to bedrock. It was a big lake that covered what we now call Morgantown. And what happens is they get compacted, pushed together, and cemented. I've talked a lot about SiO2 or quartz. Quartz is an amazing natural cement in nature, and it holds a lot of sedimentary rock together. Not all types, but a lot of it. Okay, so how can we tell the relative ages of rock? I'm not talking about numbers. Relative age just means this one's older than that one's younger than this one. That's what I mean by relative age. So we look at the position of undisturbed rock. You cannot go to the river, bring me a rock and say, how old is this? I don't know. I don't even know where it washed in from. But with undisturbed rock, we use something called the law of superposition. And the law of superposition states that the bottom layer is oldest, the top layer is youngest. And that's all that means. I just taught this to my 9th graders. The bottom layer is always oldest. And just think about making like a layered cake. You put the bottom layer goes first. And this all deals with something called relative dating. All right. So if we look at this, we see we see vertical layers. It looks like, and it's true, these rocks were tilted completely on end. This, of course, is in West Virginia. Where do you think this is? You had to just take a stab at it. It's close. It is. It's over in the mountains, a little bit further along than that, but yes, it is close to Seneca Rocks. It's over in the mountains of West Virginia. So if the rocks are tilted like that, it had to happen that they were laid down and made rock. And then we had what was Proto-Africa came and kind of collided with Proto-North America and tilted them. So there was pressure, squeezed, and the rocks were tilted. Let's see again. The draw. Where do I lay my stuff? There we go. So if rocks are tilted up like this, or folded, I should say, like this, what shape, what letter does that remind you of? Yeah, looks like an A to me. That's good, because that means it's an anticline. And then the valley of the original mountains would have been like this. To me, it looks like a smile, and that's a syncline. So I get my anticline A and my smile for a syncline. Now it's hard to tell when these rocks are straight up and down. It is hard to tell if we are looking at an anticline or a syncline, because we don't have the rest of the rocks to look at. Most likely that is the plunging edge of an anticline. So it would have been coming down from a mountain, but that's neither here nor there. All right. So what do the layers indicate? Well, the different layers can talk. They don't really talk, but the different layers, you can read these rocks, and you can read them from top to bottom or bottom to top, geographical or geology. Or you can read it like a table from one end to the other to see how things kind of happened. Well, let's read these layers from bottom to top. What do you notice about this layer right here? It is lighter in color. Does anybody see chunks of other rocks? Okay. Well, if you're getting these big pebbles of other rocks, that means something really fast moving water is the only thing that can move big chunks of rock. So when these rocks were finally settled down, that there had to have been a storm, a really fast moving, high energy environment that would cause this sort of rock. And over time, as we move up, I start to notice, oh, look, there's no more sections like that, which means that the environment had settled down, that it was calm, and whatever caused this was no longer happening. And so, and the thicker the layer, it either means giant storm or it happened for a really long time. And then the thinner the layers, the shorter period of time it was laid down. And so basically you're looking at the energy. Energy like, oh, lots of big storms, or energy without, you know, that's a really fine grained rock. Like I can't really see any kind of lumps, bumps in it. And so that's a pretty calm environment because it's probably made from clay or silt. And so that's like a suspension, like in if you ever walk into the creek, the bottom is kind of soft. And that's because there's a lot of clay and silt, but it's calm, it's on the edge. All right. So I want you to look at the rocks now. So get out your samples. Make sure you keep them in the right bags. All right, so Delaney and Heather, they are getting out the samples that go along with the picture of the outcrop I showed them. Let me see if I've got a picture of it on the screen. No, I don't. I'm sorry. You guys are just gonna have to kind of wait for a second. No. I'm talking to my online people. All right, but this is the outcrop that they're looking at right now. And they are taking out rocks from each of these samples. And they're making some observations. And they're going to put them in order with the youngest sample, number 1, at the bottom of their table. And they're going to put the oldest, I'm sorry, the youngest at the top and the oldest at the bottom, which I'm not sure why. And then they're going to write down characteristics of the rock. Yeah, the top is the youngest. And the bottom is the oldest. Got your sample 1.
No. Sample 5.
Sample 5 will go at the top, so it'll be the youngest.
Okay. Let's see what it's called. That's fine. 4, 3, 2, 1.
Yes. I know. That's
I didn't realize this was
geology flips you upside down.
I just didn't realize it's so it goes from the highest number to the lowest.
Right.
And thought-
Now I understand what they did.
Yeah, what do we do with these 2
Nothing yet.
of this and how many?
Right.
So we write like our observations.
Yeah, just write your observations.
Yeah.
No, oh my goodness, no, I'm gonna help you with that.
One's cool and that's 4.
Yeah, and that's truly, that's the only one I would expect anybody to know.
So number 4 is.
Yes. All right, for those of you at home, I'm just walking around with the rest of the class, looking at their rock samples, and they're just writing down characteristics of the rock. Some people feel like they know that one of the rocks is coal, and they're right. But the rest of the rocks they may not be familiar with. And I'm going to show them ways to identify which rocks they are. So if you just kind of bear with me as we do the lab. And Delaney and Heather, the good news is I'm not collecting this for a grade. It's just to help them take notes on these rocks. So you're not missing like a lab grade.
Okay, thank you.
You're welcome. And you thought Easter was yesterday. Seriously, it feels like it's coming from above. Sorry, I'm going to help.
I'll see you there.
I'll see you there, yes.
I really really hope nobody except our class ever listens.
I'll save you a seat.
All right, one thing I'd like for you to do is test all of your rocks with a couple drops of acid. It's hydrochloric. It's like the same stuff that's in your stomach, only much weaker. So it will not harm you.
What are we looking for?
A reaction. Some kind of chemical reaction. Then you'll probably know it if you see it.
It's too hot, too tight.
Careful of your eyes.
This one's kind of mixed through.
Nothing.
Do we have two of the same sample?
Right, I hope not. Possibly. Let's see. Okay, and what's the other one you think is the same? Yeah, this is not the same as that. They do.
Oh, we got something over here.
Okay, yes. So,
Sample two.
all right. So who all found, go ahead and test. Always. Where's the rest of this?
Oh,
All right,
that's.
try that.
You're gonna be doing Alita. It's your favorite.
Oh,
That's the acid.
oh, that's good.
This is the.
Yes. So
Oh.
if
Two
it's,
eggs on a skillet.
Sample two.
so sample 2 chemically reacts with hydrochloric acid.
What's it there?
Wow, dude.
So sample 2 is CaCO3, AKA limestone.
Two is limestone.
So that is sample 2. Sample 2 was formed in an ocean environment. And what you see, limestone is simply the shells of all these dead little critters.
Wow. That's hard.
It is.
Well, this type of
I love that you
acid.
respond to all my comments.
You're like right up front.
What's the acid?
Hydrochloric acid, or just HCl. So the hydrochloric acid interacts with CaCO3. So hydrochloric acid, what has to be an acid reacts with a what? So this is very basic. That's why you can use limestone to combat acid mine drainage. They put limestone, crushed limestone in creeks to try to neutralize the acid mine drainage.
Would the minerals that we worked with last Monday, would the acid interact with them?
Yes, if you had calcite, which we did, but I don't think I have
Is
enough.
that the one that was, we used to wrap with our nail, calcite, is there like the little?
The little rhombus,
Gotcha.
and if we would drop acid on that, it bubbles like crazy.
Does it really?
And if you're over in the mountains and you see white streaks going through the rock, that is just pure calcite, which also means that you're looking at limestone. All right.
What do we put these two?
Should we put like the basic?
Like I'm looking at that and I'm like, how did I leave that out?
We can just.
Okay, you can do that. But it's just that one.
So this one was basic. Do you want
Yeah,
us to
the
put that?
limestone.
You want us to put like CaCO3 in this one?
I may use that on the test, but I will also say limestone. So it's not anything that you have to know. It's just something that sticks in my brain. I can't get rid of. All right. So let's look and see what else we had. So is everybody pretty positive that sample 4 was coal? Okay.
This one, the liquid's not green. Is that?
Not sure what's going on with that. That is weird.
They're not supposed to do that? Oh, that's good.
No clue. It's some kind of impurity. So which one is this? Sample three. Let's start at the top of sample 5. Where is it? Okay, so sample 5. Let me come over here. Sample 5 is like a bunch of little rocks, whoops, stuck together. So we call this a conglomerate. It's a conglomeration of different kinds of rocks. That's a good question. All right. So what kind of energy would that, that's a depositional environment, means what's the environment like when it's deposited? So what kind of energy are we looking at? High energy or low energy? Very high energy to get all those rocks tumbled together. And then they would be cemented by major cement, SiO2. So like a quartz cement is usually what holds together a conglomerate. Not always.
SiO2, is that what we write on the middle column?
You can, I'm not sure. I accidentally erased what I asked for in the middle columns.
It's fine.
And it was 2012, the last time I taught this. So I don't know what I was thinking. Just some extra note space. All right. And where's sample number 4? That was coal. Sample number 3.
Right here. Is this one?
Ah. So sample number 3 breaks in these tiny little layers, thin, thin, thin. You can break it, it doesn't react. It's pretty fine grained, which means we can't really see all of the oh my gosh, the sediments that are in there. We call that shale.
Oh, shale.
Oh, shale.
So that's low energy?
Yeah, shale comes from pretty low energy because it is made from silt and clay.
Is coal also low?
Oh yeah, it's a swamp. So it had to exist like undisturbed for a long time. And every 7 feet of decomposed plants gives you 1 inch of coal. So little trivia for you. Like you wouldn't have to know that.
Are we ever gonna run out of coal?
Oh yeah. I mean, like it's being made, in the earth now, but we're not going to see that.
Right.
But
Serious.
yeah, we'll run out of coal, we'll run out of that stuff. It just isn't replenished in the same speed that we have. And aha, the last one. Can you see the sand grains in number 1?
Yes,
Does it feel sandy?
yes.
It is a sandstone. Oh, maybe that was what was in there. That's okay. So you should have.
Should that be on the
Do we need to write this?
The only thing I do want you to write is plastic means that, sorry about that. Plastic means that it has grains that we can see, and it is formed from the natural cementation of grains. Non-plastic means that it either came from a biological environment on the earth or a chemical environment. So like limestone and coal, those are both biological, because the limestone is just the dead shells of all the critters that ended up on the seafloor. And then rock salt and gypsum are these secondary minerals. I talked to you about secondary minerals that aren't formed directly from magma. Rather, they're formed from chemical reactions after the fact.
We not do gypsum.
No, we did not do gypsum because gypsum, have you ever seen the thing for mesothelioma? All those commercials for that. Gypsum causes that, so I don't bring it into class anymore. Yeah.
What was number 3?
So yeah, so gypsum actually is like asbestos.
And then number 5 was the long one.
Yeah, the conglomerate.
Oh my God, stop. You just kind of said that.
All right. So in these notes that I'll post for you, these are like the different symbols that you'll see. Like if I ever draw a picture, don't count on that. But if I ever draw a picture for you, sandstone looks like sand. Shale looks like little lines because, you know, they lay in tiny little layers. Siltstone, it looks like Morse code. Conglomerate just looks like a regular conglomerate, lots of rocks.
I really forget.
You don't have to memorize this.
Well, I try really stressed because that's all on this page, like that last sentence.
You said we need to memorize that?
No, you do not.
Can you go back one slide for 2 seconds? I can just take a really quick, probably.
Oh, that one?
Yep.
And remember, this is always going, like, I'm going to transfer this to YouTube and upload it for you.
I just like to have it on my phone. so
Ab-
I can do it really quick.
Sure. All right, guys. We are.
That went pretty good.
All right, so today, do you know why? This is why. Because my other job, we're on spring break. And so I gotta sleep in until like 9. That's okay.